Welcome to this presentation of Chemistry in STEM. In this presentation, we'll look at different ways that chemistry can be placed into various real-world situations to apply chemistry in the context of STEM education. So let me quickly review what we're going to cover in today's presentation. First, I'd like to share with you some of my personal experiences from when I was working in industry. And it is all of these experiences which I'll use as a basis for designing a number of chemistry labs that would place scientific theory into an appropriate real-world context. Second, I would like to talk a little bit about what STEM is, as there seems to be a lot of confusion surrounding the nature of STEM education. Next, I would like to give you some examples of some real-world uses of chemistry that you could try using in your class to apply chemistry in an authentic cross-curricular way that would solve real-world problems. These examples would include how to conduct a water analysis using the same methods as health and safety lab technicians would use, the use of chemistry in photography, and this is a great way to create cross-curricular lessons that will create rigorous academic learning outcomes. And finally, how we can recover precious metals such as gold from e-waste. And this would also lay the foundation for some excellent philosophical debates about the environmental, social, and economic impacts of our actions. So let's start with big idea number one, drawing on experience. One of the best ways to design and build authentic projects and curricula is to draw on lessons that you've learned from either personal or professional experiences. Therefore, I'd like to share with you some examples of how my experiences from working in industry have provided me with some invaluable insights into chemistry that can be applied to everyday problems. And I'm going to show you how we can use this knowledge to create authentic learning opportunities that uphold the ideology of STEM education. So I informally started my company in 2002, and by 2005 my company was officially registered and I was operating under an official federal tax ID. Now, my company was a small private consultancy firm that took on a large number of different projects over the years. But in 2010, my work in 3D imaging technologies took me to Korea, and by 2012, I had patented the world's first 3D reflex microlens imaging technology. Now, if you're interested in this work, you can always review the patents should you like. I've placed the appropriate reference numbers for both the US and WIPO patent offices up on the screen. But my work in 3D imaging took me into some interesting and unexpected markets. Although I would have never imagined it at the time, my work in 3D imaging brought me into the realm of cosmetics. Yes, you heard me right. My work in 3D imaging brought me into the world of cosmetics. Although these two things seem completely different from one another, the company that I was consulting for had numerous business operations that all involved a single supply chain. This supply chain started with importing raw materials, mostly from China, but also from America, Japan, and Germany. And many of the materials were imported, would be refined and then resold as, such as titanium dioxide, tin oxide, ferric oxide, and so on. Now, the first thing that we did was to test the quality of these raw materials. And if the raw materials contained a concentration of less than 5 parts per billion of lead, then the raw materials could be used for cosmetics. However, if the lead content was greater than 5 parts per billion, the materials would be diverted to industrial applications. These applications included automotive paints and the development of electronics. Therefore, depending on the quality or the quality control process, the materials would be used to create cosmetics or electronic products, and that's how my work in 3D imaging brought me into the world of cosmetics as well. Now, this aspect of my work in Korea did give me an amazing opportunity to learn something new, and I can use these experiences as inspiration for designing projects that apply chemistry in authentic ways to solve real-world problems. And that is exactly what STEM is all about. Now, I can't go through everything that we did, but I want to focus on a few key chemical compounds that were critical to our work to illustrate how real-life experiences can be invaluable to developing authentic STEM lessons. So the most important chemical compounds were titanium dioxide, tin oxide, ferric oxide, and mica. Using these compounds, we created several different mixtures that would get used by a wide variety of cosmetic and industrial applications. Although we had hundreds of combinations, here's a brief overview of some of the most important formulations. So our Crystal White series included a high sheen pigment that utilized titanium dioxide and a secondary formulation which used tin oxide to create a pigment that had a slightly warmer color tone. Next, the most popular pigment from our iron metal series used aluminum potassium silicate, or natural mica, in combination with ferric oxide to produce a red tone. And this pigment would be used a lot in the production of cosmetic products such as blush. And finally, our premium series used natural mica in combination with other compounds that we've already discussed, with my favorite pigment being part of our diamond series, and this actually used calcium sodium borosilicate. So you might have noticed from the previous slide, titanium dioxide was a key component in many of the key product offerings that we had. Now, titanium dioxide has a high reflective index, and this results in a brilliant white pigment that is often referred to as a perfect white. Some of the applications of titanium dioxide include cosmetics, sunscreen, and even toothpaste. Moreover, its high reflective index and UV resilience makes it ideal for a variety of applications, as harmful UV rays are absorbed and converted into heat energy. Therefore, sunscreens that are designed for infants or for individuals with sensitive skin are usually based on titanium dioxide formulations, or sometimes based on zinc oxide formulations as well. The next compound I want to talk about is talc. Now, talc is more commonly referred to as baby powder and has a low luster appearance that ranges from translucent to opaque. On its own, talc is greasy to the touch and is a whitish gray color. It can even sometimes appear greenish as well. It is often used in cosmetics and baby powders as it has astringent characteristics which helps reduce rashes. However, talc can be tricky to work with as it's not water soluble, but it can be dissolved in dilute mineral acids. And finally, I would also like to talk about secrete, which is also known as natural mica. While there are many different types of natural mica compounds that are available on the market, we used aluminum potassium silicate. Untreated, natural mica produces a low luster pigment which does not absorb oils. Therefore, colors may fade if skin is oily, but it is good for lighter colored foundations and it can be used in concentrations as high as 100%. When treated with dimicone, a non-toxic silicone-based polymer, natural mica will have a high luster value and improved water resistance. Higher reflectance does mean that lines will become more noticeable due to the higher contrast values, which will enhance the perceptions of lines. This makes this formulation unflattering for older individuals, however, it does help absorb oils, so colors do stay truer for longer. When treated with magnesium myostrate, which doesn't absorb oil, the natural mica formulation will create a compound that's well suited for dry skin types as well as darker foundation colors. Because of its increased adherence to skin, improved wear resistance, and its high binding power, this formulation is ideal for decorative cosmetics. However, this composition is unsuitable for individuals with oily skin, as the oils will cause colors to fade. Now, without revealing too many trade secrets, we would also apply a silicone coating to many of the pigment products lines that were destined for use in cosmetics. This silicone coating would add hydrophobic characteristics to the various compounds. The silicone coating would be applied as a liquid mist to the pigment as it was being mixed, and this process would happen slowly to ensure evenness and consistency. A low heat would also be applied to evaporate the solvent, which would also ensure that the mixing process would not produce clumps. The whole process would take about 30 minutes per batch and used an alcohol-based solvent. So why did I tell you all about my unexpected foray into the world of cosmetics? Well, making lipstick in class can be a fun way to get students to learn how to use lab equipment while also applying basic chemistry skills to create a real-world product that they can actually use. Now, while students are not going to be able to mass-produce cosmetics using the compounds that I discussed earlier, specifically as they'll not be able to conduct the necessary quality control and testing requirements that are required to ensure the final product is safe for human use, it's still possible to simulate the big ideas by creating organic approximations that would accurately simulate a real product. While exact chemistry will not be needed in this example, students would still need to practice various lab skills, which make this kind of activity a great point of entry project for middle school students. So let me explain how you can make lipstick quickly and easily with your students. Everything that you'll need is currently listed on the screen. Now, the first thing that you'll need to do is to melt beeswax, shea butter, and coconut oil in a glass beaker. But make sure you do not use a direct heat source to melt your binding agents. Therefore, it's best to surround a beaker with hot, not boiling water, and to keep in mind that the materials will melt quickly as they have a low melting point. Next, once melted, remove the mixture from heat and add ingredients such as scents and colors. Then, once all the ingredients are mixed, pour the mixture into a lip chap container. Be sure not to fill the mold all the way up to the top, as the lipstick will expand slightly as it cools. And then leave the lip chap for about 30 minutes so that it can thoroughly cool all the way through. Now, while you can use inexpensive silicone molds, you may also consider using professional grade stainless steel molds as well, just like what we would use to create pre-production testers when we experimented with new color formulations in the lab. Either way, with minimal prerequisites, you and your students can apply chemistry in an authentic way to create real-world products in class. And this kind of activity should really help get some of the younger women in your class interested in STEM education as well. And that brings me to big idea number 2, which is trying to understand the true nature of STEM education. So you're probably thinking, what other experiments can I do in my classes that will apply chemistry in a variety of real-world contexts? And this is what STEM is all about, using science, technology, engineering, and math skills in context through a variety of real-world lessons. But there's so much confusion around STEM education nowadays, so it's important that we take a moment to develop a common understanding of STEM education. So it's widely accepted that the acronym STEM stands for Science, Technology, Engineering, and Mathematics, and I don't think anyone in the audience would argue with that analysis. It seems that everyone knows what STEM is, but there's a lot of confusion and uncertainty surrounding STEM and all of its derivatives. So let me delve into this a little bit more. Now, I think most people are aware of Bloom's taxonomy, but for those of you who don't, Bloom's taxonomy is a classification of the different levels of thinking or cognition, where knowledge is at the bottom, and as we develop our understandings, we can start applying what we know and eventually start synthesizing and evaluating the results of our own thought process. And I think this is an important thing for us to stop and think about, because everyone seems to have knowledge of what STEM is, but very few people have a deeper understanding of the true nature of STEM or what it should be. And we as educators know that there's a big difference between knowledge and understanding. Now, because of the confusion surrounding STEM, there has been a number of criticisms that have been made of the framework over the year. And this has led to a number of STEM derivatives. Now, while these criticisms are valid, they only identify a problem without understanding what caused the problem in the first place. And this has resulted in a number of STEM derivatives which have created an incredibly confusing landscape for educators and administrators alike. So let's look at some of these acronyms. So we have STEM, and we also have STEAM, which adds creativity through the arts. But we also have STEMs, which recognize the importance of social sciences by adding the S at the end of the acronym. STEMMA, which adds managerial arts and was first proposed by Harvard University. Next, we have ESTEAM, which recognizes the importance of developing English literacy development. Now, as trend indicates, countries with higher English proficiency are more innovative as they have access to a wider breadth of current research materials from the global community. So this idea of an ESL curriculum into the STEM framework is important for non-English speaking countries so that students can access a wider range of research materials, which will help them go on and become more innovative. And this leads us to another derivative known as STREAM, which adds reading or research. And finally, we have STEM with a double M, which was created by Dr. Stephen Meyer and Reverend John Gretz, who added the values of Christian missionary to the mandate of STEM education. And this ties in with the idea that the World Economic Forum had as well, but from a slightly religious standpoint. And it also corresponds with the ideas that the Chinese have with STEM plus 四肢教育, or moral education. So this definition is true to the initial definition of STEM education that was first introduced in 2001 by Judith Ramley, who at the time was the director of the National Science Foundation Education and Human Resource Division. So let's read through this definition together. STEM education is an interdisciplinary approach to learning where rigorous academic concepts are coupled with real-world lessons as students apply science, technology, engineering, and mathematics in contexts that make connections between school, community, work, and the global enterprise, enabling the development of STEM literacies and with the ability to compete in the new economy. Wow, this definition is very verbose. So I'm going to highlight a few key words here. Interdisciplinary approach, rigorous academic concepts, real-world lessons, apply science, technology, engineering, and mathematics in context to compete in the new economy. So STEM is actually linked to economic goals, to help students compete in the new economy. And we can't really forget about this connection because this is really the main driving force at the government level for STEM. But let's try simplifying this definition. STEM solves real-world problems using science, technology, engineering, and mathematics. So this is the simplest definition that I can make to define STEM, and I've never had anyone make any objections to this definition. However, this perception of STEM education, which I have represented by a red box, is incredibly limited, and it's really going to limit our understanding of STEM. So we need to add more depth if this is our working paradigm. So let's expand these boundaries and add a bit more depth to our understanding of STEM education before moving on. So if our aim is to solve real-world problems, then the problems that we explore should be authentic. By extension, so should the solutions to that problem. And finally, the approach should also be cross-curricular. But professionals in the STEM field are also addressing real-world needs in society. So we should also add this as a qualifier. And these industry professionals are leading innovation through creative problem solving. So now we have a definition that is much simpler to understand with easy to read bullet points. And it still upholds the ideology of the original definition that we looked at a moment ago, while being a lot easier to read and understand. However, there's still one last point I should emphasize. Although skills are often learnt in STEM, the focus of STEM education is not on the development of job skills for a labor market. And I think that's an important thing to recognize. So I'd like to share this graphic with you that I made to really show this idea of how all these different concepts of STEM education interconnect, from the various core subjects that STEM is comprised of, to the critical industry sectors that STEM education is supposed to support, the educational theory that interconnects with STEM education, and the various stages of cognitive development. As you can see, the core subjects, science and math, act as columns supporting everything that STEM education represents, and these core subjects are supplemented by the interdisciplinary subject areas. Now, STEM acts as a merging point for rigorous academic concepts that we learn in those core subjects as we apply these concepts in real-world lessons that apply these theories in contexts that help students prepare for the new economy. However, there are so many critical sectors in the economy that are represented by STEM. So after we see the merging of all the core subjects, we also see STEM starting to branch out into a number of specialized fields of study, which all fall under the STEM umbrella. This creates an hourglass shape as we take multiple subjects, bring them all together, and then spread out again as we go on to specialize in specific fields of study later on in life. And that brings me to Bloom's taxonomy. As you can see, we always start with knowledge, and as we learn the basics, we start to understand abstract concepts. These concepts could include how to solve an equation or how molecular bonds work. And these are all important concepts to understand if we're going to start applying theory in real-world lessons in a STEM program. So you can see that the core subjects really need to precede STEM because we cannot apply math and science before first understanding the basics. Then in STEM, we can start applying what we've learned in context to solve real-world problems and then go on to analyze the results. And finally, later on in life, industry professionals are required on a daily basis to synthesize seemingly unrelated concepts to solve complex problems in the real world. And of course, they'll need to evaluate the effectiveness of those solutions as well. Next, we can look at where we're going to get the greatest impacts in STEM. And since students really need the foundations in math and science before they can apply these concepts, and critical thinking skills are critical to STEM education, you'll find that STEM will have the greatest impact when it's taught in the middle and high school levels. And this notion also corresponds well with what we know of Piaget theory of cognitive development, which indicates that logic and abstraction only really starts at age 12 and continues all the way through adulthood. So now that we have some common understanding about STEM education, let's look at some classroom examples to determine if these class projects represent the true nature of STEM education. And then let's look at ways we can modify our lesson plans to ensure that we're achieving the desired learning outcomes. Let's start with this STEM project here. This was a project that was used to promote a school STEM program. Now, what grade do you think that this project is for? What about now? This was actually a grade 12 honors chemistry project where students were learning about creating water-resistant paints. Now, you might be thinking, just as I am right now, that this activity isn't appropriate for that grade level. But the school was proud of it because they thought this was a good example of STEM education because the students had engaged in hands-on learning. Now here are some more images from that post, and you can see that these grade 12 students are in a well-equipped chemistry lab creating paint using craft glue and ground-up colored chalk. But we're probably asking ourselves, where's the real chemistry? This lesson was supposed to be a lesson about making colored paints, but designing authentic STEM lessons is really difficult, especially if a teacher has never worked in industry before. Now I should state that this teacher was absolutely amazing in chemistry when it came to teaching theoretical concepts, but they had a limited understanding of how science would be applied to solve real-world problems in industry. Now there's so many ways that we could have made this project more appropriate for grade 12 students, so let's take a look at some of these ideas. So here I have some examples of what we could have done instead. Here on the left I have referenced how we could look at different chemical compounds that would allow for a thermochromatic effect to be explored. That is when the color of something changes due to temperature as a result of a reversible chemical reaction. Next, on the right, I have an example of how you could create ferric oxide to create a color pigment. Now for reference, ferric oxide and titanium dioxide are actually the key component in the manufacturing of makeup products such as blush. So we already have a few options that we could use to improve this one project. But let's take this a little bit further. Now that we have some pigments, we can then explore different chemical methods to convert this pigment into a usable paint. First, we could look at how to use different chemical solutions to create a binding agent and then chemical solvents. Second, we could look to our past to see how some of the greatest minds of our time created masterpieces such as the Sistine Chapel. At this time, paints were made using pigments such as ferric oxide and lapis lazuli, which were ground up into fine powders. These pigments were then mixed with egg whites to create a molecularly stable, organic compound that could last for centuries. And in all honesty, these methods were actually superior to our current manufacturing processes in many ways. So with a few simple changes, this project could easily be redesigned in a way that would make it much more meaningful. Next, I want to talk about fads versus enduring knowledge, or more specifically, looking at developing sustainable curriculums that can withstand the test of time. Here I have a post showcasing a project that I personally really like, CO2 dragsters. And this is one of the best-selling projects from companies such as Hygienius and Pittsco. Now, while some STEM products have only been around for a few years, this one product has been sold in the US for close to 70 years now, well before Steam even existed. For example, here's the Pittsco guide from the 1990s that I used as a student when I studied technology. But CO2 racers were popular way before then. In these final examples, you can see some of the do-it-yourself kits from the mid-1950s. And these kits were popular activities at the time as they helped kids get interested into aerodynamics and propulsion during the US-Soviet space race. Now we can see the influence of this idea of rocket-propelled vehicles as a major driving force in our modern society, even to this day. From the development of the fastest land-based vehicle, which was essentially a rocket on wheels, to our modern maglev train technologies. All of these advancements came from the study of propulsion and aerodynamics. And that brings me to my next example. While over-the-counter do-it-yourself kits like this one provide educators with easy, ready-made projects that could be implemented with little to no preparation, these kits tend to offer very little towards achieving the desired learning outcomes of established curriculums. However, rocketry has so many wonderful grade-level extensions for senior school students. For example, here's a balanced chemical equation for a combustion-based reaction that can be used to create a stable, solid fuel rocket engine. Now let me explain what's happening. First, we have potassium nitrate or fertilizer, and this is mixed with regular table sugar. As long as this chemical mixture does not come in contact with a flame, it's relatively stable. However, it's capable of creating a powerful combustion-based chemical reaction that will create a large amount of thrust. And this reaction will result in the formation of an inorganic compound, carbon dioxide, and water. Now, as an instructor, I wouldn't give my students the balanced chemical equation. Instead, I'd start by reviewing about how to balance a chemical equation, and then have them balance this equation on their own before checking their work and moving on. Then, in order to create the most efficient rocket fuel, students would need to determine the molar mass of each compound so that they can determine the correct ratio of each. With all of the math done, they'd then be ready to move on and create their own rocket fuel. Now, as it stands, this project would have them apply chemistry in an authentic way. However, it still wouldn't have the students apply the scientific method, and I have a perfect way to do that. What would happen if we added aluminum to the mixture? Would it improve your rocket's performance? And what evidence can you provide to support your claim? In this case, students would need to formulate a hypothesis that they could then go on and test. Now, in theory, adding something that is not necessary to balance the chemical reaction is a bad thing. However, adding aluminum to rocket fuel is the exception to that rule. Let me tell you a little bit more about this phenomenon. In the early 1950s, Kenneth Rumble and Charles Henderson conducted a series of experiments where they added aluminum to conventional rocket fuels. The results of their experiments indicated a dramatic increase in the exit velocity of combustion gases, so much so that it brought solid rocket fuels into similar performance levels as liquid fuels like kerosene and liquid oxygen. Due to the research into chemical propulsion methods, the US Navy was able to significantly increase the range of ballistic missiles and orbital rockets. Now, because this was a bit of a trick scenario, almost every student's hypothesis will be disproven. However, this will give them a great opportunity to conduct some internet research to look for answers. And the students should be able to find the answers to this question as the initial research has been declassified and can easily be found on the internet. But what about testing such a hypothesis? Although we could use analog test equipment, we now have the benefit of digital force meters, which open up a world of possibilities. We can easily record and export precise data from our experiments directly to the computer, which is great for collecting data. So it's even easier to do this kind of experiment than it used to be in the past. Now you can see what a simple setup for testing homemade rocket engines would look like in this photo. And finally, if your school has a metal shop, you may also consider manufacturing your own rocket engines using a small metal lathe. As you can see from this example, when you develop fully cross-curricular approaches to teaching and learning, which is what should be happening in STEM, you'll find that your projects will go much deeper into the core curriculum. And that type of in-depth and insightful exploration, that's what's going to make students more competitive in the new global economy. And that is what STEM is all about. And that brings us to big idea number 3. This is where I'd like to share some specific examples of how chemistry can be used to solve real-world problems, and how we can use these examples to create authentic lessons that apply chemistry in an appropriate context. So the first real-world example I would like to talk about is water analysis. Now, water seems simple enough, but it's actually a highly complex substance. This is because water acts as a medium for numerous chemical reactions that can occur in tandem with other chemical reactions, as you'll see in just a moment. So students are often taught how to use test strips like these or litmus paper in class, and most people are only aware of these simple over-the-counter test solutions. However, commercial testing requires a much more sophisticated approach, and personally, I don't ever recall a single time where I used test strips while working in industry. And that's because test strips only measure key metrics. They lack precision, the results can easily be skewed by irregularities, and they do not show the correlation between how different metrics interact with one another. And all of these factors make test strips relatively unreliable. They're perfectly fine for teaching the basics in controlled situations, but outside of the classroom, they have limited real-world value. So chemists will often use professional testing reagents or digital meters so that they can collect accurate and precise readings. For instance, experienced environmental engineers and lab techs will often conduct tests on location using things like this dissolved oxygen test kit, which uses a specialized reagent. Alternatively, things like this dissolved oxygen meter may also be used. And many schools have similar equipment such as Pasco or Vernier lab equipment, which students could use to conduct similar tests within an educational setting. And these kind of water tests are critical to the preservation of our hydrological cycles and the management of our fresh water supply. And to illustrate this idea, here's a photo I took on my last trip to Yunnan province in China. One thing that caught my attention were these floating water oxidation devices. These devices increase the amount of dissolved oxygen in the lake water, which helps aquatic life such as fish thrive, while also reducing algae blooms. As a result, the water in these lakes has drastically improved over the years to what you see today, crystal clear blue lakes. Now, this would be a perfect STEM project for students to undertake: design, build, and test a water oxidation device. However, this project would be more in line with engineering practices than chemical testing applications. For instance, testing dissolved oxygen is relatively simple with a digital meter, and it's also straightforward with reagents as well. So the test itself is not difficult. However, what makes environmental engineering demanding is the continuing testing and follow-up. In these situations, the technician or engineer will likely test the oxygen level daily for an extended period of time. In the case of Yunnan, this project's been going on now for over 10 years. So this kind of data collection analysis is not practical for a high school science lab. Therefore, we need to look for something that has a little bit more immediacy. And many schools have access to a great resource that they can use to conduct some real-world water analysis that's probably more relevant to the students. So many schools have access to a swimming pool, or at the very least, tap water that could be tested. Now, if the school has access to a swimming pool, the students can test the water, identify any potential problems, and then identify what corrective measures are needed to ensure that the pool meets all health and safety regulations. However, if a school does not have access to a swimming pool, they could still test regular tap water to determine the suitability of the water source in use in a commercial swimming pool, and then analyze what treatment options would be necessary to optimize the water before use. Either way, the students will still be able to conduct a number of experiments to test the water samples and collect all of the necessary results. However, I should warn you, although most people think that testing pool water is a simple task, it's actually quite demanding, as you'll see in a moment. So as I mentioned before, test strips are not particularly useful as they lack precision and the results can easily be skewed. So commercially operated pools are required by law by most developed countries to conduct a series of professional tests on a regular basis. In this example, I'm showing BioGuard, which is a company that I have a lot of experience working with. But other companies also provide commercial testing solutions such as Lamont, Taylor Technologies, and Fisher-Sy. Now, as you can see by this lab setup, testing pool water to meet government health and safety regulations is no joke. So let me take a moment to explain the different tests that must be conducted by a lab tech to ensure that all health and safety requirements are being met. The first test that's needed is a TDS test, or total dissolved solids. With this test, a small amount of water is poured into either an analog or digital device. The TDS meter will then provide a reading by measuring the conductivity of the dissolved ions. It does this by setting a small electrical charge through the sample, and it measures the EC, or electric conductivity, in what's called Siemens. Now, if you're unfamiliar with the term Siemens, it's the SI unit of conductance, and it's equal to 1 reciprocal ohm. Now, ideally, the lower the TDS level, the better. And while there's a difference in the desired chemistry of both vinyl and concrete pools, the ideal TDS level is the same for both in this case. It's also important to note that not all pools use chlorine as a sanitizing agent. Some pools, particularly in Australia, use salt. However, regardless of the sanitizing agent being used, testing the TDS level of the pool is an important first step, as it will help the technician identify what type of water sample is being tested, while also getting an overall impression of the quality of the water. Essentially, it helps us determine if the water is healthy or not. The next test is total chlorine. This test is typically done using a 10 milliliter vial of water in either a glass or plastic vial. A reagent is added, which will change color depending on the concentration of chlorine. That sample is then held against a white backlight and is compared against an accurate color chart. With BioGuard, this reagent comes as a pre-measured tablet, which is dissolved in the sample. This ensures the addition of the reagent is perfectly measured every time. While other companies such as Taylor use a liquid reagent, which is a little bit easier to use. However, the droplet size can vary slightly depending on how hard you squeeze the reagent bottle. The next test is free chlorine. Now, both chlorine tests should be done simultaneously so that the total and free chlorine values can be compared. Ideally, these two values should match. However, there are numerous situations which can cause a discrepancy between these values, and these scenarios would indicate a serious problem that needs to be addressed. Furthermore, if the chlorine level exceeds 5 parts per billion, or 5 parts per million, the results of the other tests will be skewed. While professional tests using reagents can accommodate for this, test strips cannot. As a result, high chlorine values result in test strips getting bleached out, which skews the results, thus making them unreliable and unsuitable for any commercial testing purposes. The next test that needs to be done is pH. Now, if the chlorine value exceeds 5 parts per million, you can get a phenomenon called bromophytal blue. In this case, the pH reagent turns a dark purple, which would indicate a very high pH. However, in reality, the pH is usually very low in these situations. Therefore, it's very easy to misinterpret these results and make the wrong recommendations to address the problem. That being said, if you know the chlorine level is high before conducting your pH test, you can act accordingly. All you need to do is to add some chlorine neutralizer to the water sample before adding phenol red to the pH to test the pH level of the sample water. The next test that's required is for manganese, which can damage the finishing of the pool surface. And after that, additional metals such as copper are tested for. Now, copper can enter the pool water in a few different ways. If the pH level of the water is very low, the acidity of the water can start corroding pool equipment such as the pump and filter units. However, this is becoming less common as most companies are trying to avoid using metals in places that are exposed to water. Alternatively, copper gets added by people all the time, particularly when the pool is neglected by the owner. In the event that a large algae bloom occurs, many pool owners turn to copper sulfite, which is a highly effective chemical agent which is used for killing algae. However, and it can also be purchased at many department stores. Now, while the addition of copper sulfite does address the immediate issue of the algae bloom, it does create a number of other serious problems that need to be addressed before the pool can be used again by swimmers. And finally, the last metal to be tested for is iron. Since this reagent smells like sulfur, or is based on sulfur I should say, it smells like rotten eggs. So you're likely going to have students complain about the smell of this test if you do it in class. Next is to test, the next test uses a chemical titration to test for total alkalinity. For this test, you'll measure 100 milliliters of water using a graduated cylinder. You'll then pour that water into a large beaker which has a volume no less than 250 milliliters. Then, using a magnetic stir plate and a tablet, you can slowly stir the water sample during the titration. Start with a slow flow of reagent until you start seeing a color change. Then reduce the titration to a steady drip. Monitor the color of the sample, and after every drip, you'll monitor the color of the sample after every drip. And the moment the sample changes from a bright orange to a dark orange color, stop adding reagent. This change will be very abrupt, and once it happens, take the measurement from the burette to see how much reagent was used. And the final test is to determine the calcium hardness of the water. This test also uses a chemical titration, but the reagent will go from a vibrant pink to a dark purple in this test. Now, as there's no way to practically remove calcium from the pool water, the only way to address calcium hardness is by draining some of the existing water and adding fresh water to replace it. Typically, the calcium level of a pool is balanced when the water is added to the pool for the first time, and it's never adjusted after the fact. However, calcium hypochlorite is a popular economy pool shock. This form of granular chlorine has a low chlorine content per mole, slow to dissolve, causes the water to go cloudy, and is also molecularly unstable, which can lead to the compound spontaneously combusting. Quite often, if you hear about someone's pool equipment exploding, it's because they use calcium hypochlorite instead of other compounds that are more stable and effective. And that brings me to the idea of safety and the importance of understanding chemistry, as we normally just take things for granted. So at this point, I'd like to show you a short news clip from ABC that illustrates the dangers of ignorance.
Well, it's almost summertime officially next week, and you know the heat has a lot of families heading to backyard swimming pools. But tonight, we have a warning if you're treating that pool yourself.
This comes from a family in Greenwood that's still cleaning up today after some pool chemicals reacted in their home earlier this week. It caused a large explosion and sent the couple to the hospital for treatment. Naomi Pescovitz explains what happened and what they say you should know.
The couple who lives here consider themselves experienced pool owners, and they treat their own pool all the time, which is precisely why they want to share their story with others. They never thought these 2 bags could do this much damage.
This one I poured in first and poured this one on top of it, and when it was just the powder, there was no problem. And then I added water, and when I added the water, it just exploded. I mean, it really did. It was so fast, within seconds.
2 different brands of swimming pool shock treatment turned into a cloud of toxins in the kitchen.
I dropped the pitcher into the sink, and it started to shoot. Like, it sounded like mortar. It just was a pow, pow, pow.
The sink dropped. Pictures flew off the walls. Days later, the chemical is still splattered everywhere. The couple didn't want to share their names, but they do want other pool owners to know what happened.
It was shock. We thought it was all kind of the same thing, and so you just kind of add it together, and you throw it in your pool. It's water, so you add water. You don't think there's going to be any kind of a reaction, and we added water, and there was a major reaction.
They could be upwards in the range of $20,000 to $30,000 of damage in the kitchen.
The chief of the Barkersville Fire Department says this was simply a mistake, but one that could happen in any home.
Our homes are filled with dangerous chemicals, whether you have a pool, cleaning supplies, any other thing. And it's, you just got to be careful mixing those and even how you store them.
Despite some respiratory problems immediately after the explosion, both husband and wife are fine, though the loud blast burst the woman's eardrum and left burns behind her ear. She was wearing this rain jacket, which shows how much worse it could have been.
Really, that's what took the brunt of it, was that coat. That's kind of the epitome of what could have been my face.
Now the family is left with all this cleanup, dealing with insurance, even a hazmat crew coming in, but thankfully it's all material and everyone's okay.
And this brings me to a critical safety point. Always add chemicals to water and never water to chemicals. Now, I don't expect that your students would ever be adding chemicals to the school swimming pool. However, this is one tip that's incredibly relevant to any lab experiment. And finally, while the dangers that chemicals such as calcium hypochlorite have cannot be understated, there is another chemical that's commonly used by many pool owners that's even more dangerous. Regrettably, people use it because it's cheap, and often the people that use this chemical have limited education and lack an understanding of its destructive power. This chemical is sodium hypochlorite, which is more commonly known as liquid chlorine. Often used in conjunction with chemicals such as hydrochloric acid, these 2 chemical compounds can result in violent explosions that will produce chlorine gas. Now, for reference, this is the same compound that was used during the World Wars to create chlorine gas in the trenches and in the gas chambers. It only needs to be mixed with one other commonly used pool chemical, and that's it. Now, cautionary tales aside, the next thing that students will need to do is to analyze the results and make the necessary calculations. This is a great time for students to apply the study of 3-dimensional geometry, or they could also use any of these formulas to quickly estimate the volume of a variety of standard pool shapes. Alternatively, depending on your student's grade level, they could also use a summation formula like what I've shown here from this textbook example. Then, with the volume of a pool determined, students would then be able to review instructions for each chemical and determine the correct amount needed to correct any imbalances in the pool's chemistry. Furthermore, the pool needs to be balanced in the same order that we conducted the tests on the original water sample. And finally, one of my favorite inventions in the pool industry, saltwater generators. First invented in 1972 by Cascade Pools in New Zealand, these little devices can take standard table salt, turn it into a usable form of chlorine before reverting it back to salt again, making this a sustainable and environmentally friendly solution to pool chemistry. Now, while this method of pool sanitation is not common in North America, countries like Australia, which are relatively isolated from their trading partners, tend to use saltwater generators almost exclusively. But environmental and economic factors aside, the required salt levels needed for the effective generation of chlorine is about 3,000 parts per million, which makes the chemical composition almost undistinguishable from saline, thus making the natural chemistry of pool water ideally matched to our own physiology. Now, for reference, for anyone who's not familiar with the medical sciences, saline is commonly used in IV drips when people are dehydrated or suffering from severe vomiting or diarrhea. So you might think that the chemical reaction that happens in saltwater pools is relatively straightforward. Salt is converted into chlorine and then back to salt again. Think again. The actual process that's happening is quite complex, so I'm going to break it down a bit. First, salt is dissolved in water, which causes the molecules to ionize. Next, using a process of electrolysis, the charges of the sodium and chlorine ions are stripped. This will result in the formation of a metallic sodium and chlorine gas inside the generating chamber. And this process is accomplished by using a 12-volt electric charge and a series of polarized platinum blades. Now, the use of platinum makes these generators incredibly expensive to buy outright, but it's the only metal that can withstand the corrosive nature of the chemical reaction. Now, first, the metallic sodium is going to instantly react with water, causing the formation of hydroxide and hydrogen gas. And the second reaction that will happen will be the hydrolysis of aqueous chlorine gas, which will result in the formation of hypochloric acid, and these two reactions will happen simultaneously. This will be followed by the dissociation of hypochloric acid, which will result in the formation of hypochlorite and hydrogen gas. So the net of all of these reactions is this. Now you're probably saying, wow, that's complex, but that's only the first half of what's happening. So what happens next is the reaction will result in the formation of sodium hypochlorite, and this will eventually break back down into water to create salt, a small amount of hydrogen off-gassing, and a small buildup of hydroxide over time. As such, the entire reaction will cause the pH of the pool to rise. However, the natural tendency of a pool is for the pH to drop over time as a result of sweat and rainwater, which are both acidic. However, if natural causes do not keep the pH in check, the use of hydrochloric acid can be used to help regulate the pH. So as you can see, there's something that is seemingly simple actually requires an in-depth study of molecular chemistry. And that's what STEM is all about, learning rigorous academic concepts while applying science, technology, engineering, and math in context. And this will really help students prepare for the new global economy. And that brings me to my next example, photography, which is where I started my career in 2002. Now, while most people think that photography is a simplistic art form, history will tell us something completely different. So I want to start by sharing these examples with you. It's one of the most unique requests that I ever received while operating my company. It was to photograph every piece of glass artwork in a museum collection. However, this glass was unique as the artist was known for using uranium in many of his works. Yes, you heard me right. Some of these works are enriched with uranium. Now, you cannot see the effect of the uranium under normal light. However, if we apply high energy particles that are outside the visible light spectrum, the uranium will absorb that energy and irradiate it back out as visible light. Much like the energy transfer process that happens with the Earth as ultraviolet rays are converted into infrared rays, which help keep the planet warm. So this is what these artworks look like in the dark. Spectacular, if you ask me. But one thing that you'll notice is that we were unable to tell which one of these examples had uranium based on what we could see with the human eye. So the only way that I could go about doing this project for the museum was to understand chemistry, physics, and the art of photography. So then, now that I have your attention, let's look at some of the chemical advancements that have been made as a result of photography over the years. Because many of the famous photographers throughout history were in fact scientists. And it might also surprise you to know that most students that study photography at the university level tend to fail out of these programs because they lack the necessary math and science skills to understand advanced photographic concepts. So the ambrotype was the first type of photographs. With this method, photographers would take a simple glass plate and coat it with a thin layer of iodized collodion, which then was dipped in a solution of silver nitrate. The plate would then be exposed to light inside the camera while it was still wet, which made this method very difficult to conduct, particularly when on location. Moreover, exposure times for prints varied from 5 seconds to more than a minute depending on the brightness and the speed of the camera lens, and this also made photographing objects more difficult. The glass plate was then developed and fixed through a series of chemical processes, and finally the process resulted in the formation of a negative image, which would then be viewed by reflecting light against a black background, which would make the image appear as a positive. This is because the clear areas would look black and the exposed opaque areas would appear relatively light. Moving on to Louis Daguerre. The invention of the daguerreotype advanced photography, as this process had significantly better quality and was more durable than the glass ambrotype, and it was also easier to work with. Now, the daguerreotype would form an image on a polished silver surface. These highly polished silver plates were then made light sensitive using iodine fumes, which would produce a light sensitive silver iodine coating. This light sensitive silver plate would then be exposed by light inside the camera. The latent image would then be developed in a purpose-made developing box using mercury vapors. Then, after development, any unexposed silver halide would be removed using a mild solution of sodium thiosulfate. While the ambrotype was difficult to handle and easily broken, and the daguerreotype far too toxic, especially as it requires the use of mercury vapors, it goes without saying that both of these methods would be unsuitable for students. However, photographic methods that use silver iodine can provide students with excellent opportunities to explore cross-curricular learning opportunities. Even without fancy camera equipment, students can explore the scientific and artistic aspects of black and white photography using a pinhole camera. In this situation, photographic paper is placed at the back of a box in complete darkness. A pinhole is then made on the opposite side of the box and is then covered with an opaque piece of tape. The tape is then carefully removed to start the exposure and is then replaced to stop the exposure at the end. The print can then be developed in a darkroom or even a bathroom sink, providing that you do not expose the paper to any white light. Now, while Kodak's bankruptcy in 2012 was a big blow to the black and white community, which loved the D76 developing solution, it did not stop professionals and enthusiasts alike. And it's because of the legendary D76, and this is because the legendary D76 solution can also be made at home or at school using some common chemical compounds. First, start by adding 750 milliliters of distilled water at a temperature of 52 degrees Celsius. Then add 2.5 grams of methyl and 5 grams of hydroquine. Add 100 grams of sodium sulfite and anhydrous. And the last chemical that needs to be added is 2 grams of borax granular. The final step is to add an additional 250 milliliters of cold water to bring the solution down to 20 degrees Celsius, which is the optimal temperature for developing film. Now, if all of that sounds too complicated, don't worry, because the rights for D76 were bought by another company, and it's still made under the Kodak name to this day. So you can easily buy pre-made D76 developer through a variety of commercial resellers if you'd prefer. Now, after the developing stage has been completed, the chemical reaction needs to be neutralized by a process known as stop bath, fixed, and then washed. So the stop bath neutralizes the alkaline developer, thus halting the development process. Now, stop bath is typically comprised of a dilute solution of acetic acid, so you can actually create a simple stop bath using household vinegar. However, a solution of potassium or sodium metabisulfite can also be used. Next is the fixer solution, which removes any unexposed silver. The fixer solution contains sodium thiosulfite, sodium sulfite, and sodium bisulfite. And finally, the wash. Now, there's nothing special about this as it's just running water, but some photographers do like to use a dilute soap solution known as PhotoFlow to reduce the required wash times and conserve water. Now, as I mentioned before, you can still buy black and white chemicals online, and there's actually a resurgence in new products coming to the market these days. And part of this is because there are still some things that you can only be done using chemical-based photographic solutions. And this makes film the go-to solution for a number of specialty and artistic scientific niches. For instance, two products that I've used that are very specific are Ilford nuclear emulsion film and infrared films. And I'm particularly fond of Fujiacro's film in combination with Ilford fine grain developer for ultra high resolution imaging. Now, if you're interested in some of these scientific applications of these specialty products, Infrared film is great for astronomy and aerial surveys of vegetation studies, but it can also be used for military reconnaissance as well. And nuclear emulsion films are great for investigating charged particles and can also be used for finding structural faults due to material fatigue during safety audits. So as you can see, there's a lot of math and science in photography, and I haven't even got into some of these scientific principles yet either, such as pushing and pulling film, reciprocity, the Scheimpflug principle, or any of these mathematical theorems. And these are all things that students need to learn when studying advanced photographic concepts at the university level. And finally, I'd like to explore the chemical processes for the recovery of precious metals and adapting these methods in a way that would be appropriate for high school students to explore. Furthermore, the idea of precious metal recovery would also reinforce numerous lab skills and theories, but it would also tie in with the humanities as we explore the social, economic, and environmental aspects of our decisions. Now, regrettably, most e-waste is not recycled, but as you'll see in just a moment, the recycling process is not overly environmentally friendly either. So by exploring precious metal recovery methods, we can actually start getting into the philosophical and ethical debates about the consequences of our actions as well. But one company that could change the way we look at e-waste is Mint Innovation from New Zealand. Yep, the same country that invented the saltwater generator. Now, Mint Innovation has developed a revolutionary new method of recovering precious metals such as copper, tin, gold, and palladium using microbes. While this process is not something that we can explore in a high school setting, it's a great case study to share with students either before or after learning how traditional chemical processes work. Now, if you want to do an e-waste lab, the first thing you will need to do is to collect scraps that contain precious metals. For reference, older computers do tend to be better for this kind of experiment. But what components have the highest concentration of gold? Well, the north and south bridges contain microscale scale gold wires and gold-plated traces. Female connector pins that are plated with gold. PCI and memory slots that have gold-plated pins inside. Integrated circuits contain gold wires inside. And monolithic ceramic capacitors contain both silver and palladium. And any visible gold-plated pins are worth mentioning. Now please note that you'll want about 6 kilograms of scrap so that you will be able to collect enough gold to make this kind of a lab viable. It's also a good idea to minimize the addition of circuit boards that contain little to no gold in your scrap, so it's recommended that you cut the gold fingers off the edge of the PCB boards so that you don't waste your time on a scrap that won't provide any precious metals. Now, while mimicking commercial e-waste recovery methods would be ideal, the physical limitations of a classroom learning environment are somewhat prohibitive due to the lack of time, space, and resources. However, we can draw inspiration from these commercial practices and simplify them for use in the classroom. So let me start by analyzing the difference between these two approaches. First, official recycling processes require a large number of exotic chemical compounds. These compounds allow the chemical process to completely dissolve the entire structure of the circuit board and IC chips. As a result, the superiority of this process will allow for the precious metals to be recovered. Once the entire circuit board has been dissolved in acid, different chemical compounds will then be used to precipitate each metal out of the solution in a specific order, based on its electron affinity and reactivity level. Please note that it's very important that each metal is extracted in the correct order to ensure purity of the recovered metals. These metals will include copper, lead, iron, and the more precious metals such as silver, gold, and palladium. Once each of these metals has been precipitated out of solution, it will then need to go through a number of refining processes before smelting. While this process is too complex to explore in school, a simplified process where only the exposed gold is recovered can provide students with an authentic learning opportunity. This type of e-waste lab also works well in schools that have a breaker space in the primary school, as these activities tend to result in an accumulation of e-waste that can then be used by students in the senior school. Now, to get started with an e-waste lab, you'll need the chemicals and equipment listed here. You'll need the following chemical compounds: hydrochloric acid, hydrogen peroxide, nitric acid, sodium metabisulfite, stannous chloride, and sulfuric acid. Furthermore, you'll need a number of standard lab items, but there's nothing out of the ordinary in this list. And finally, there's a few things that you might want to use to make the recovery process easier. These items include a small DC air pump, which can be used to agitate the solution, and vacuum filtration to accelerate and improve the filtration process, and a magnetic stir plate with heated bed to make it easier to mix different solutions. And finally, please note that a practical lab like this should always be done in a well-ventilated area. Therefore, the use of a fume hood is strongly encouraged. Now, the process that we're going to cover is only capable of recovering the exposed gold that's found on the connecting fingers of circuit boards. Therefore, it's best to use a paper guillotine or tin snips to cut the fingers off and send the remaining circuit board off to a commercial recycling facility. Once you've collected a large amount of gold scrap, you should cut it down so that it fits in the bottom of a 3-liter beaker, and then add 1 liter of hydrochloric acid. You can use an air pump to help agitate the solution as well. The clear hydrochloric acid will start turning green as it reacts with the various metals. Now, printed circuit boards, or PCBs, are layered with the gold connectors being overlaid on top of other conductive metals. Our objective here is to allow the hydrochloric acid to start dissolving the underlying metals. After about 10 minutes, slowly add about 100 milliliters of hydrogen peroxide. Now, the ratio between acid and peroxide should be 10:1. This will cause a chemical reaction which will produce off-gassing, heat, but more importantly, it will create bubbles which will agitate the solution, which will help to dislodge the gold from the surface of the PCB board. And this will also be important if you're not using an air pump to help agitate the solution. It is also recommended that you cover the beaker to contain the fumes and avoid any unnecessary dilution of the acid. Let the reaction continue for a minimum of 12 hours. Therefore, it would be practical to let the reaction go overnight, and then students can come back to the next step of the experiment the following day. At this point, the solution will have changed from a green to a dark black color. Add another 100 milliliters of hydrogen peroxide. This will act to further dilute the solution and to rejuvenate the chemical reaction. Repeat this process twice over a 72-hour period. Due to the time it takes for this process to occur, you will likely want to split your lessons. Have students spend a few minutes addressing the practical requirements of the lab, and then the remainder of the class addressing theory. This could include updating their lab books with observations, procedural notes, and also covering the theoretical aspects of the lab. After 72 hours, the solution will be ready for the next step. At this stage, you can pour the solution into a clean beaker. Keep the solution though, as it needs to be filtered to remove any gold before disposing of the waste solution. Next, use thick rubber gloves and a water spray bottle to wash the PCB scraps. Make sure that you inspect all PCB scraps to ensure that there's no gold remaining on the surface of the PCB boards, and if there is, you'll be able to easily rub it off manually at this point. With the scraps thoroughly washed, you'll now be ready to filter the blackened acid to catch any fine particulates that are still remaining in solution. Pour the solution into a funnel with a filter, or better yet, use vacuum filtration unit. Also, be sure to pre-wet the filter for optimal results. Once the entire solution has been filtered, you should be left with large gold particulates in the beaker and some finer gold particulates that have been caught in the filter. You can now dispose of the initial acid solution. Please note that there will be dissolved metals such as iron, lead, and copper in this solution, which could be recovered using more advanced recovery techniques. However, these methods are much more complex and require the use of many more chemicals. Moreover, as gold is the most valuable metal and time is limited, it's practical to only focus on extracting gold in an educational setting. Next, carefully remove the filter and place it in a clean beaker, as it will be full of gold powder. Then let the filter dry. At this point, you'll have a beaker that has a gold sludge and another beaker with a filter paper full of small gold particulates. However, the gold will contain a lot of other contaminants. Next, we'll remove any other contaminants from the gold residue. Use a 1 liter beaker and add all the gold residue that has been collected, and then add 200 milliliters of hydrochloric acid. Then add small amounts of nitric acid using a dropper, pipette, or burette so that you do not end up with an excess of nitric acid. Gently warming the mixture using a magnetic stir plate with a heated bed will also aid in this reaction. At this point, the gold will start dissolving and you'll see red nitrogen dioxide fumes. Please make sure that you avoid breathing these fumes in. Once all the gold has been dissolved, filter the solution again, removing any bits of fiberglass and plastic from the solution. Be sure to thoroughly rinse your beaker, funnel, and filter with water until the solution runs clear, as the residue will contain gold. The next thing that you will need to do is to create a saturated solution of sodium metabisulfite. Using a magnetic stir plate, slowly add sodium metabisulfite granulars to water until the solution can no longer accept any more. That is, when the granulars no longer dissolve and start accumulating at the bottom of the beaker. Then add your filtered gold solution to a large 1 liter beaker. Be sure to rinse your flask with water, as the solution will contain gold. Then add the sodium metabisulfite to the gold-bearing solution. The sodium metabisulfite will react with hydrochloric acid in the solution, which will create sulfur dioxide gas. The gold ions will be attracted to the sulfur, which will cause them to fuse together and drop out of the solution as a metallic precipitate. Allow the heavy gold particulate to settle at the bottom of the container. Wait a minimum of 4 hours or overnight. Next, conduct a stannous chloride test to see if there's any gold left in solution. The remaining solution should be translucent brown. Carefully pour the waste beaker without disturbing the gold particulate at the bottom of the beaker. Check the waste with stannous chloride one more time to make sure that there's no gold in it before disposing of the waste solution. Then, rinse the gold sludge with warm water and allow the gold powder to settle. Once all the gold has settled, carefully discard the wash water. You'll be left with a gold mud at the bottom of the beaker. At this stage, you could dry the powder, or you could process it further. My recommendation is to process it further. To continue filtering out the impurities in the gold, you'll need to add 400 milliliters of hydrochloric acid. Apply medium heat and stirring. As the hydrochloric acid boils, it will react with any remaining metals that are in the powder, and the solution will start getting darker, most likely as a result of iron. Let the solution settle and then perform another stannous chloride test. If the acid has dissolved any gold, you'll need to add small amounts of sodium metabisulfite to precipitate the gold out of solution. It's important that you add it slowly, as you do not want to knock any other metals out of solution at the same time. Therefore, you'll need to keep conducting stannous chloride tests to help you identify when you should stop adding sodium metabisulfite to the solution. Then pour out the waste and rinse the gold powder with hot water again. Let the gold settle and pour off the wash water. At this point, you could melt down your gold, or you could purify it one more time by conducting another round of hydrochloric acid, followed by medium heat and stirring, followed by small amounts of nitric acid. After about 1 hour, you'll have an orange solution. And then you allow the solution to cool before adding sulfuric acid. This will react with any dissolved lead, which will precipitate out as a fine powder. Vacuum filter the solution and be sure to rinse your beaker, funnel, and paper with water, as they'll contain gold. The lead precipitate will be stuck in the filter. Then add sodium metabisulfite to precipitate the gold out of solution. Then conduct another stannous chloride test to ensure that there's no gold left before discarding the waste solution. Then rinse the gold powder with hot water again. Once the gold is settled, pour off the rinse water, let the gold powder dry, and then pour it into a crucible. Use a torch to melt the gold and then pour the molten gold into a small jeweler's mold. You'll now have a small gold nugget that will be probably around 20 carats. So I hope that you liked this virtual in-service and that you found it informative, and that you've taken away a number of ideas that you can use to design authentic learning opportunities that apply chemistry in a variety of real-world contexts. So thank you again for sharing your precious time with me to attend this presentation of chemistry in STEM education.